dat moet even gekopieerd worden. Dus je maar 1 terabyte extra schijven.
Je kunt gewoon een USB harde schijf rekenen.
Ja, die moet eigenlijk even aan.
Wat zijn de inmeldingen?
Ja, dat ga ik je even doorgeven.
Stuur het in de app om.
Ja, het PC-wachtwoord is... Wacht, ik heb hier natuurlijk gewoon laptop. Even kijken, waar ben je nou?
Wie is Sama?
Dat is Rodney.
Oh, hij was toch ook onderweg?
Ja. Dat heb ik weer. Even kijken, dus ik ga niet het wachtwoord wat op zeggen, want dat weet iedereen het. Jammer jongens.
Nee, zet het even in een appje of zo. In een documentje.
Ja, het staat op de desktop, maar dan moet je wel eerst in het systeem kunnen.
Ja.
Stefan weet deze ook, trouwens.
Ja, maar die zit op de Groomstraat de komende 2 dagen.
Oh, die draait alleen het weekend doen.
Die draait vrijdag, zaterdag, zondag.
Oh. Nou, dus dit is deze dan. En het enige wat je hoeft te doen is, je hebt de OBS Studio, die staat op de desktop, die start je aan. Dan gaat dit allemaal starten, dan laat hij waarschijnlijk dit allemaal in.
Ja.
En dan moet je inderdaad...
Camera gaat ook niet aan en zo?
Ja, dat wordt allemaal geregeld door OBS. En dan doe je gewoon start streaming en start recording. Want dan slaat hij het zowel in Twitch, dus dan stream je live en dan slaat hij het ook op de D-schijf.
Ja.
Je moet alleen even kijken in de gaten houden, want het is niet een hele grote schijf.
Ja, dat is dan.
Dus er is een kans dat je deze...
Die gaat voor zondag wel vol zijn dan.
Ja, dus we moeten even zorgen dat we een USB-schijf of zo hebben waar we het even tijdelijk op kunnen zetten of op het netwerk of dat soort zaken.
Dus deze dan, waar staan ze op nu?
Ja, nu staan ze op de E-schijf.
Dus dan halen we een externe schijf erbij.
Ja.
En dan kopiëren we die files
dan hoef je deze even...
naar die andere file, als backup zeg maar. En dan kan deze gewoon gebruikt worden steeds als recording.
Ja, maar als je dus zou kopieert, moet je wel de recording uitzetten en de stream uitzetten.
Nee,
dus nog steeds stream, maar dat doe je dan natuurlijk
nog een eind van de dag of zo. Ja. Voor nu, hoe lang kan die nog opnemen?
Ja, sowieso de hele dag. Je kan de hele dag opnemen en streamen. Dat is geen probleem.
Nee, dus we moeten eigenlijk voor morgen even zorgen dat we een extra
Eigenlijk
unit hebben.
Ja, dus als we even een externe USB... Ik heb dat...
Assen even...
ja, precies.
in de kamer naast.
Daarom. En dan...
Oké. Nou ja, straks is op, dat kan ik wel...
Ja, er is ook een chat. Die hoef je in principe niet... Daar hoef je in principe niks mee te doen. Maar het is wel handig dat als er vragen zijn of zo, dat...
Ja, ik zal even kijken bij de berichtjes.
Ja, precies. Dus dat loopt allemaal. Jullie stemmen zijn allemaal online. Ja, nee, maar dat heb ik net gedaan. Maar Randy stond daar. Dat heb ik net gedaan, maar er stond dus voor het raam. En toen was hij dus buiten beeld. Dus je moet hem even instellen op het moment dat als hij daar gaat klussen, dan moet je hem even aanpassen.
Ja, ik weet het. Ja,
nee, ik heb ook geen idee.
Maar wat handiger zou zijn, denk ik, is dat we op een moment een tafel naast die zetten. Want hij is zoveel op zijn tafel. Dan kan hij de monitor daar zetten. Dan kan je het ook met zijn camera heen.
Ja, maar het beeld moet wel het scherm moet wel in beeld blijven natuurlijk.
Ja, precies. Dan hebben we een cameraatje ook in die binnenkant van de monitor.
Of je op zijn PC ook een OBS.
Ja, zullen we dat gewoon lekker doen?
Dat is al moeilijk dat.
Weet je, dit was al even regelen. Dit is even voor nu goed en de volgende keer gaan we het even anders aanpakken. Ja, ik zou het moeten doen. Als je inderdaad dit doet en je zou hem dan moeten bewegen. Maar hij wordt dan blauw, hè, want dan herkent hij je commando. Kijk, zie je nou, en maar dan moet je wel bewegen. Als je ziet dat hij knippert, moet je bewegen. Maar.
Ja, voor mij ook die voorliefste dingen.
Ja, heel even. Ja, en ik wilde, I didn't want to let Randy do it because he's going to look like this.
What do you mean? Do you have to tell the camera something?
Yeah, this is a gesture. You can pan the camera, but if you're going to do this, it's rather silly.
No, I'm not.
So we'll just keep the camera steady, and France will check the stream every now and then. Occasionally.
Okay, so reach into your little bag of parts or sample bag of components there and pull out this thing right here. And let's start learning about stuff that really does fail. Again, just by way of review. We've covered resistors first. We've measured resistors. You can see how easy it is to do. Oh, by the way, you can attempt to measure resistors in circuits. And in fact, you could... Oh, where is it? Hello? Alexei.
We got some casualties.
Possible. Come on.
We're pulling the cup out. People coming out.
Okay.
I think it was the cup we're pulling out.
Oh, that's probably smoking.
Yeah, that's go all the way downstairs.
Oh, okay.
I'm still smoking.
Sorry, yeah, no, I forgot about it. I do want to mention that you can attempt to measure resistors in circuit. You can attempt to test everything in circuit, really. But don't be surprised if things do not check properly in circuit. And the reason for that is that there's so much other stuff connected to it. I'm trying to check that resistor, but perhaps there's another resistor here hooked up to it, another resistor here, some other component here that we don't know about, and all of those things affect the reading. My philosophy is, when in doubt, take it out. You will unsolder lots of parts to test them. Let me just mention this, and I'll mention it probably a bunch of times before the end of the class. Part of testing and soldering stuff is you unsolder a part that you think is bad, you test it out of circuit, and you only discover, it's actually good. You are not doing anything wrong. Don't think that you failed just because you pulled out a part and it's actually good. It is completely normal to troubleshoot that way. That's the way we really troubleshoot stuff, is by taking it out of circuit. And, you know, as I've gotten more experienced, I wouldn't say advanced, but more experienced, I kind of know what to expect. But you guys will be pulling out lots and lots of parts to test them, only to find out that they're good, perfectly good, and solder them back in. Don't think you're doing anything wrong. It's a perfectly normal way to troubleshoot. About half the parts you pull out will probably be good, especially in the beginning. As you get more experience, you kind of learn. So resistors hardly ever fail. Next, we're going to look at this component right here. And there's also a couple on that strip of parts that are in the kit that you're going to do this afternoon. And the actual official name of this part is aluminum electrolytic capacitor. It's an aluminum electrolytic, L-Y-T-I-C, capacitor. People just refer to it as a capacitor, but there's tons of different kinds of capacitors. Lots of them don't fail, or rarely fail, but the aluminum electrolytic capacitor is almost guaranteed to fail. Almost 100% of the time, eventually they fail. And as you know, that's why folks in this industry and this hobby, this passion, I guess you'd say, often replace things. They install a cap kit. This is the answer to lots of people. They have a bad monitor. The first thing they want to do is change every electrolytic capacitor in the whole monitor, which there's nothing wrong with doing that. And if I find a couple of bad electrolytics, well, maybe they are all bad or whatever. But if I'm just trying to figure out what's wrong and fix something, it's real easy to mess up. If you're changing 25 capacitors all at once, it's real easy to make a mistake. We're going to talk more about that as we get through the class later on. But this is by far the number one failure. So, what is a capacitor? Well, I have a capacitor that I use here for demonstration purposes. And I have a 9-volt battery here. So right now the capacitor is discharged. I'm going to charge the capacitor. All I'm going to do is connect it to the battery. Just going to momentarily connect it to the battery. It's now fully charged. Capacitors, they charge up really fast. Watch what happens when I connect this lamp across the capacitor. Ooh, exciting, huh? You want to see it? I know you want to see it again. Right? So again, I'm just going to connect the capacitor. It is polarized. We'll talk about this in just a minute with a positive and negative lead, so I'm being careful. But it only takes, and in fact, I've probably held it on much longer than I need to. It doesn't take very long to charge up the capacitor. And when I put the lamp across the capacitor, you can see that it lights up, but then it discharges. So it's kind of like a rechargeable battery, but it doesn't last very long. Well, you may think that that's a bad thing, but that's actually a really good thing. Before we go any further with capacitors, let me tell you that the main quality of a capacitor's health is not measuring how much it holds. It's like a water storage tank. Instead of holding water molecules, it's holding electrons. That's the difference. I mean, it even looks like a water tank, right? The important thing about a capacitor is not so much how much it holds, but its ability to quickly take in the charge and quickly give it back out. And you'll find out why that's so important as we go through the class. And what fails in the capacitor, which we'll talk about tomorrow, is it loses its ability to charge quickly and it loses its ability to discharge quickly. That's the main problem with these, what they're called aluminum electrolytic capacitors. Well, before we go any further, I want to chop one of these things open. I want to chop one of these things open and show you what's inside the capacitor, and it'll kind of give you a better handle, a better idea of what's happening when it actually fails. The more we can understand about the actual failure mode, the better. So it's called an aluminum electrolytic because it's mostly made out of aluminum. It has an aluminum can. The leads themselves are made out of tin. But inside there's some aluminum as well. So let me just kind of chop it open and show you what's inside. I'm just chopping the can. So I can also pull off this heat shrink. The plastic that's over the outside of it is heat shrinkable tubing. You have some of this in your kit, in your tool kit there. Heat shrinkable tubing. It's plastic tubing that when you put it on and hit it with hot air, it shrinks down. let's pull this out. So here's what's inside the thing. So it's some kind of rolled up thing, as you can see here. And it's wet inside. There's a possibility, I haven't tried it with this capacitor, when they squeeze it, you might see a little drop of liquid coming out the front here. Let's just see if I can do that. Oh yeah, definitely. I'm getting in focus here. You can definitely see how this little bit of liquid kind of came out of the thing. So let me take it apart a little further. And it has this rubber plug on the bottom here, so I'm going to pull the rubber plug off. Maybe. My hands are all slippery with this electrolyte. The liquid that came out of something called electrolyte. We'll talk about it in just a second. And it's something that's all rolled up, and it just has some cellophane tape on the outside holding it together. So I'm going to cut the cello tape off. Let's take it apart a little further. There we go. So I'm now going to unroll the thing. So I'm going to unroll it. I'm going to unroll it. And 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 unroll it here. And you can see that the component lead is actually spot welded to this thing. Or spot crimped, I guess. I guess you could call it spot weld. These two pieces of aluminum foil you see here, there are two pieces of aluminum foil, and you can't really solder to aluminum. So the component lead is hooked up like that. It's just kind of crimped or spot welded on there. It's two pieces of aluminum foil, and they're separated by this paper. And this paper is soaked in something known as electrolyte. I'll write it on the board in just a second. So these two pieces of aluminum foil are technically referred to as the plates of the capacitor. Plates, like a plate that you would eat off of, a plate of the capacitor. And they're called the plates because when they originally made the first capacitors, they were in fact two, well, I won't even take this one off. They were in fact two metal plates separated by a piece of glass. And in fact, the very first capacitor was invented here in the Netherlands, in Leiden, right down the street at the University of Leiden, and it was referred to as a Leiden jar. The very first capacitors, and then they finally figured out what electricity really was and made the first kind of capacitor that we would think of as a modern capacitor. It was two metal plates separated by a thin piece of glass, which happens to be technically known as the dielectric. You don't have to know that. And that's what makes something a capacitor. Anytime you have two things that can conduct electricity and you put them real close to each other but not touching, they form an energy storage device, which we call a capacitor. So it has these two aluminum foil plates, and they are polarized. A capacitor, an electrolytic capacitor, almost all of them are polarized. If you look real carefully at your capacitor, you have two leads. Notice that one lead is short and one lead is long, or one lead is shorter than the other. And where the short lead is, you'll see a stripe down the side of the capacitor, and you see negative signs. We mark the negative side of the capacitor. So it's marked two ways. One, by which lead is the shortest. It's not that different. Short like that is the negative side, and this stripe on the side. If you connect an electrolytic capacitor backwards, it will blow up. Not maybe kind of blow up. Not, it might blow up every now and then. It will blow the F up. It'll blow up. It'll sound like a firecracker going off. There'll be a big cloud of white smoke. You probably have to change your underwear. I mean, it really It really can go up. You have to be careful to the point of paranoia when you put in a capacitor. You have to absolutely make sure of the polarity of the capacitor. When you look at the printed circuit board, it is marked somehow. It's silkscreened somehow with the polarity. Typically what you see is something like this, where they'll silkscreen the outline of the capacitor, and here are the holes where the capacitor goes in. And you might see that half of this has hash marks on it. That's the negative side of the capacitor. In more modern stuff, you'll see they just put like a block down here, kind of a filled-in block. That indicates the negative side of the capacitor. You would think that they would mark the positive side. I would anyway, and they did, used to. It's not uncommon to see a positive sign like on the dots, like that. And in some older stuff, like the old Hytron power supply, I don't think there are any even working now. They just noted it with a dot, which is very ambiguous. It's like, what is that supposed to mean? I don't know. But you just have to be really careful. The chances of you having one electrolytic capacitor on something are zero. So, I mean, if you pull it out and go, oh, which way did I pull it out? Just look at the other ones and you'll see how they go in. But do be extremely careful. When I put in a capacitor, I'm just so careful. I put it in, I bend the leads over so it doesn't fall out. I turn it upside down to see which lead is the shortest, the longest. I turn it back on top, look for the stripe. I solder it in. I double check it after I solder it. And then when I plug it in to fire it up for the first time, I do not hover over the top of anything that I've replaced capacitors on. I'm just saying, when you plug something in and you've changed caps, don't go, hey, look, I changed capacitors here. Because if you put it in backwards, it's going to blow up right in your face. And it's going to be really painful. It'll be... One of my students scared the hell out of herself. I mean, she really scared herself. I used to do a hands-on power supply repair in this class. And instead of having the students plug it in at their desk, I said, could you bring it up here and let's connect it up here. And all I use, honestly, I told you I'm a cheap and dirty technician. One of my favorite tools is this stupid thing. It's just an AC power cord. Of course, that's our plug for the United States, with a couple of clip leads on the end. We commonly refer to this as a suicide cord for pretty obvious reasons, right? Also known as a widowmaker, right? So this is how I connect up almost anything. With this, I can connect anything, can't I, to the AC power? I'm just, kind of being careful. And she hooked up the AC input. So here's the AC input. She hooked it up, and we had a power strip on the desk just like this. She plugged it in and was looking like this. And before I could even say, don't do this, this capacitor took off. It went kaboom! And it blew the can, the aluminum can. I forget where it is. Well, wherever the can went. It blew the can. It went like on a trajectory like this. And we had this acoustic tile there, and it punched a hole in the tile. And it was like, she really freaked out. I said, do you need a hug? She said, yeah. I gave her a hug. She said, do you want to sit down? Yeah. It was really frightening. So I'm just saying, be extremely cautious about the polarity of the class.
If you put it wrong and it explodes, can it affect other components or just?
Almost never. That's a great question. If you put a cap in backwards and it explodes, have you damaged anything else? Generally not. Because it's so susceptible to reverse polarity, it's the first thing that goes. I'm trying to think. That's a great question. I've never put one in backwards, so I don't know. Of course, that's a big lie, because everybody's put one in backwards. I don't, generally speaking, no. So, we have these two aluminum foil plates here. One is what we call the positive plate, and one is called the negative plate. The positive plate, let me start with the negative plate. The negative plate is just raw aluminum. It's just like aluminum foil that's in your kitchen. It doesn't exactly look shiny because it's microscopically etched with a bunch of lines that you can't see. that give it more surface area, that gives it more capacitance in size. If you'll notice, if you've ever replaced modern capacitors, replaced your old capacitors, you'll notice that modern capacitors are a lot smaller. Capacitor technology has really increased quite a bit. I mean, it's really gotten a lot better, so that we have more capacitance, as it's called, in a smaller package. Anyway, so it has these two plates. The aluminum foil, the negative plate is just raw aluminum foil, but the positive plate is insulated. It is insulated. It is aluminum, it's aluminum foil, but it's covered with a layer of aluminum oxide, which insulates it. So the way a capacitor, well, first let me draw the schematic symbols, plural, for capacitors, and then we'll talk about how they actually work. So there are several different symbols for this exact same point. I have no idea why, but here are the symbols. So the traditional way that I've seen it mostly is this. There's a straight line and a curved line like that. And the straight line is the positive side of the capacitor, and the symbol, the positive symbol is, the plus symbol is part of the schematic symbol. So this is the whole schematic symbol. Obviously that's the negative plate, that's the positive plate. But there's another version of this that's exactly the same part that looks like this. This is the same part. So I don't know, is this a Euro symbol maybe,
Yeah.
and this is American?
Yeah.
I think possibly that's what it is, or this is Japanese or something. But they're never both on the same schematic. They'll all be like that, or they'll all be like this. But it's one or the other. Every now and then on the older schematics, you'll see a symbol like this, and this makes the most sense to me. But it's the rarest used. You'll see two parallel lines that represent the two parallel plates. They are parallel, they're rolled up, but they're parallel to each other. And the hash marks inside represent that piece of wet paper which is soaked in electrolyte. It's called electrolyte. And more about that in just a second. You will see schematic diagrams for capacitors that look like this, without the plus sign on them. That is not an electrolytic capacitor. That is not what we're talking about here. I'll show you them later on in the class. They are very low failure items. The main deal is these aluminum electrolytic capacitors, and the main deal the reason that they fail is that they dry out inside. Remember I mentioned to you that the positive plate is insulated. This plate is insulated with this aluminum oxide.
Yeah.
Well, believe it or not, the negative plate of the capacitor is actually this wet piece of paper. The actual real negative terminal of the capacitor is, we call it the cathode. The negative terminal is this wet piece of paper. Well, you can't solder to a wet piece of paper, I'm pretty sure. So the way this works is that the paper, the wet piece of paper, touches the negative plate, and it has to make really good contact, and then we just solder to the wire lead that's hooked up to the actual plate. So the best way to think of electrolyte is like, if you've ever left batteries in a flashlight or something too long, the stuff that leaks out is electrolyte. The acid that's in your car battery is electrolyte. The technical definition of electrolyte is that it's what is known as an ionic solution. It's an ionic solution. And that means nothing to you, probably. The easiest way to think of it is, think of it like a liquid wire. It's more than that, but it's easiest to think of it as like a liquid wire. Like, for example, a lot of people think that water is a good conductor of electricity. You hear, well, water and electricity don't mix. Oh, but the water itself doesn't really conduct electricity very well at all. It's a bipolar compound, And it just doesn't conduct electricity very well. If I were to measure the resistance of this water, it would be millions and millions and millions of ohms. But if you make it ionic, that is, if you add a little bit of salt to it, or base, or acid, or almost anything, it will start to conduct electricity. So electrolyte is more than that. There's a whole chemical process, but it's easiest to think of it that way. So we have this insulated positive plate. We have the wet electrolyte soaked piece of paper, which is the actual negative terminal, which you can't solder to it, so that it touches the negative plate itself, which is just raw aluminum, and then we connect to that. And the reason capacitors fail is that this dries out inside. It dries out inside, and instead of us having a nice capacitor here, we have a capacitor with resistance inside. We're going to talk about this in great detail tomorrow, because you're going to make a device tomorrow that measures this. And we'll talk about it more tomorrow. We'll talk about the whole deal. But that's why, as capacitors age, they dry out inside and then they fail. Bad capacitors often look bad. That is, a bad capacitor, you'll often see that the top is domed on the top. But just because it doesn't look bad doesn't mean it's good. I'm going to mention this a lot as we go through the class, and tomorrow when we talk about capacitor testing, I'll talk about it a whole bunch, but I'll mention it right now. If a capacitor looks bad, and again, I'll show you tomorrow, if the top is bulged out on the top, it's bad. There's other visual indications. If it looks bad, it is bad. But just because a capacitor looks perfectly good does absolutely not mean that it's good. A capacitor can look perfectly good, but be totally bad. And this happens to me a lot, where people in the class will bring me a power supply and say, "Hey, Randy, 3 people have looked at this power supply. Do you think you might take a look at it and see if you can fix it?" And one of the first things I'll do is I'll point to some itty-bitty, teeny-weeny little capacitor, like maybe this little guy right there, and I'll ask them, well, that one looks good, but did you test it? Oh. You're not going to work on it. Wow. That is really weird. Oh, wait, it's connecting now. I didn't share it. I don't know why it goes off. That's bizarre. I'll point to some tiny little capacitor, like, for example, this one right here, this little capacitor down here. And I'll ask them, well, that one looks good, did you test that one? And always the answer is, well, no, we didn't think about that. It's so small, that can't be it, could it? Every part in here does something, doesn't it? Just because a part is tiny doesn't mean it's not your problem. And the small capacitors fail a lot. We're going to talk about this in great detail coming up tomorrow. About that. But for the moment, let's take a look at capacitor specifications. Testing will come tomorrow. So capacitor specification. Specification number 1, capacitors are rated by microfarad. Specification number 1 is its capacitance. And its capacitance, and it's measured in microfarads. microfarads. Capacitance in microfarads. The more microfarads a capacitor has, the more of a charge it will store. Well, in fact, that's sort of a lie, because a capacitor is really rated in something known as the farad. Whoops, Faraday straw. Oh, yeah, there's a Michael Faraday straw here? Oh, really? That's nice. You have lots of streets here that are named. Whoops. No. That are named for people. Oh, what did you do? Not Michael Faraday straw. Oops. Sorry, I'll get there eventually. This guy, Michael Faraday. So our capacitance, our unit of capacitance, is actually something known as the farad, named after this guy, Michael Faraday. He was a scientist that lived during the Victorian era in England. He used to do lectures at the Royal Academy, don't you know? And he invented lots of stuff. He invented the transformer. We haven't covered transformers yet. But he's the guy that made the first electric motor. It was a real crappy electric motor. It didn't really. It just made a needle move around. But it was the first time that electricity made something move. It was like, whoa, that's pretty cool. So they named the unit of capacitance after him. He didn't invent the capacitor, but they named it after him. But a 1 farad capacitor is humongous. A 1 farad capacitor is just a giant amount of capacitance. We use capacitance that is rated in millions of a farad, and of course micro is another one of those metric prefixes. So when we're talking about electronics and metric prefixes, we have lots of really big stuff like megohms, millions of ohms, and kiloohms. Those are big things, but we have small things too. So we use a capital letter M for mega, like megohms. We use a K for kiloohms. So those are big things, but we have small things too. For example, there's a metric prefix milli, M-I-L-L-I. Milli, of course, means divide by 1,000 or times 1,000. So you can have a millivolt is 1,000th of a volt. You can have a milliwatt. Like your phone is limited to 600 milliwatts of radiated power, so you don't fry your brain with your cell phone and stuff like that. Milli is abbreviated with a lowercase m, as you know. Like millivolts would be like lowercase m-v, like that. Megohms, millions of ohms, capital letter M, omega. So these are microfarads, and micro, of course, means divide by 1 million or times 1 million, right? Micro. How are we going to abbreviate this? We only have 2 M's in the English and the Roman alphabet. Probably in the Russian alphabet, too. It's just one in the upper and middle. So what are we going to do to abbreviate micro? So the abbreviation for micro is this psycho thing. This thing right here, that is the Greek letter mu. It's a lowercase m in the Greek alphabet. If I'm on my computer and I type a lowercase m in Arial or any font like that, highlight it and change it to a font called symbol. Symbol is the Greek alphabet, really, and it comes out with this thing, the Greek letter mu. So capacitance, the first specification for a capacitor is its capacitance in microfarads, abbreviated mu f. And if you look real carefully at the capacitor that I've given you, look at it real carefully, that's 1,000 microfarads. We don't say like 1K microfarads, by the way. It's kind of weird. But it's 1,000 microfarads, and it's abbreviated mu f if you look at that real carefully. But because the Greek letter mu looks a lot like the Roman alphabet U, you will see microfarads abbreviated, especially in older schematics, as UF. But it is not an UF. There's no such thing as an UF in electronics, I think. It's microfarads is really what they mean. Everybody with me on that? And on some really old stuff, you may even see MFD, just written out like that, MFD. But the modern stuff, it looks like that. So the first specification for a capacitor is its capacitance in microfarads. The more microfarads it has, the more of a charge it will store. And we use a wide range. You can have electrolytic capacitors that are 0.47 microfarads, just under half a microfarad, and you can have capacitors that are 6,800 microfarads, or even higher than that. You're familiar in the older games with the big giant, you guys call it Big Blue, the big electrolytic capacitor in the bottom of an asteroid game, something like that. They're huge. So that's specification number 1. Specification number 2 is the voltage rating. Now this is really important. Wake up, wake up, wake up. The voltage rating of a capacitor is not how much voltage it puts out. It only puts out what you put into it. In other words, if I have a 9-volt battery here and I charge the capacitor with a 9-volt battery, it could be a 15-volt capacitor. It could be a 100-volt capacitor. I'm only getting 9 volts out of it. Does that make sense to everybody? The voltage rating of the capacitor is not how much voltage it puts out. It is simply the maximum that it can handle. It's the maximum voltage that the capacitor can handle. And for that reason, and this is important to know, anytime a voltage rating on any component is simply the maximum it can handle, not how much voltage it puts out necessarily, you can always use one of a higher voltage rating. It is perfectly okay to use a capacitor of a higher voltage rating, and it doesn't matter how high at all, and it's not a temporary fix. In other words, well, I'll just give you an example. A little while ago, I got a service call, which for me was the ultimate service call that I just couldn't believe I got this call. Ring, ring. Hi, it's Randy. Hey, Randy. How'd you like to come to Corpus Christi, Texas? It's on the Gulf Coast of Texas. God-forsaken Texas. Hey, Randy, how'd you like to come to Texas and fix 100 monitors in a week? And I went, tell me more. I really want to know about this. So it turned out that there was this guy that he actually ran a souvenir store, and he sold seashells by the seashore and things like that. His main business was actually selling gold metal detectors. So you'd go along the beach, and find jewelry and stuff like that. That was his main shtick. But he wanted to make some extra money, so he thought that he would go to Atlantic City and buy 100 slot machines, video slots. He bought 100 slot machines. These were supposed to have been what we refer to in the casino business, I'm also in the casino business, as floor pulls. A floor pull is, the game is on the casino floor. It's operating, it's a perfectly good game. You take the money out of the cash box, you put a hand truck on it, a dolly, whatever you guys call it, take it off the floor, it's a floor pull. It was working yesterday. Should be perfect. But those bastards in Atlantic City, what they did was the boss said, hey, where do those games go to? Oh, they're floor pulls, sir. It's 100 games. We're going to send them to Corpus Christi, Texas. He said, well, they're all good. Yeah, they're all good. Don't we have some bad monitors on the shelf that fit those machines? Oh, we do. Well, why don't we pull out these good monitors and we'll just put some bad ones in? Great. Isn't the power supply good enough? Yes, sir. It's a floor pull. It was working yesterday. Don't we have a box of bad power supplies? Yeah, we do. Can we just put them? Yes, we do. How about the printed circuit board, the PC and the computer? Is that good? Yes, sir. It's a floor pull. Don't we have some bad boards in there? So anyway. So they loaded up all his machines with bad monitors, bad power supplies, bad boards. He doesn't have a technician. He runs a souvenir shop. So that's when I got the call. So I went out there, and fortunately for me, every one of these monitors was one that I was real familiar with. And there are 5 capacitors that always fail in these monitors. I mentioned to you earlier that it's experience that helps you get going really fast. So I already knew what was going to be wrong with these things. I started pulling the monitors out, and I could see someone had been there before me and replaced two of the 5 capacitors that I know fail all the time. They replaced the 2 big ones, but there were 3 itty-bitty capacitors in there that they didn't change. So for the second time now, I'm telling you that just because a capacitor is itty-bitty does not mean it's not your problem. Everybody with me on that? For some reason, people are drawn to the bigger capacitor. It's a capacitor. I'm just going to change it. I recognize it. I'm going to change it. But the little ones fail a lot. Remember that they dry out inside. I said that's really the failure mode of these things, that they dry out. Well, if it's real tiny, it doesn't, in my opinion, have any, I guess you would say, reserve juice inside. It's really a tiny little thing, and it just dries out. So anyway, so the capacitor that I needed to replace was 10 microfarads at 16 volts. And that's how you express it, by the way. Typically, when you're expressing the value of a capacitor, you express it first by its capacitance in microfarads, and then by its voltage, the voltage rating. So the one that I needed to change was 10 microfarads at 16 volts. Well, before I left for Corpus Christi, I filled this exact bag with electrolytic capacitors. I just bought some of every value, everything from a 1 microfarad up to a 2200 microfarads, and every voltage from 16 volts all the way up to 125. I bought 20 of each, which at the time, it was about $350 US to fill this bag with capacitors. And I thought to myself, I am set. I have a huge bag of electrolytics. I'm going to fix the hell out of these monitors. So I got there, and I got these 100 monitors, and they all have the same problem, and this is one of the capacitors that I needed. So I replaced those, but I could only fix 20 monitors, only 20, right? Just by throwing in these capacitors and fix 20 monitors. I still have 80 monitors to fix, but I'm out of 10 microfarads at 16. So the next thing I went up to was 10 microfarads at 25 volts, and I have 20 of those. So I still have 60 monitors to fix. The next thing was 10 microfarads at 35 volts. So now I've got 20 of those going. I still have 40 monitors to fix. Then I went up to 10 microfarads at 63 volts is the next voltage rating up. I'm almost there. I only have 20 more to fix. And at the end, I ended up using 10 microfarads at 125 volts to replace this 16 volt capacitor. But it doesn't matter. The only difference between the voltage ratings of a capacitor is the amount of insulation on that positive plate. Remember I mentioned to you that this aluminum foil plate is covered with aluminum oxide. Well, the thickness of that coating is what determines the voltage rating of the thing. So it's still a perfectly good capacitor. It just has a more insulation on it. So it's not a temporary fix. It's permanent fix. It doesn't help anything to use a capacitor of a higher voltage rating. Some people are under the wrong impression that, oh, I'm going to put 25 volt capacitors in where 16 volt goes because it'll be better. It won't. It won't. It doesn't change anything at all. You can do it, no problem at all, but it doesn't help anything to use a higher voltage. And they are a little bit more expensive. But, I mean, not much.
You see,
Most electronic components are cheap because they're made out of dirt. So parts are cheap.
in the past, I didn't have like a big stock of different capacitors.
Mhm.
So I always had the question, or the doubt, that I'm missing one capacitor of certain microfarads.
Okay.
How bad is it to? I mean, if I have one that's very close in value.
Excellent question. It's right where I was going to cover next. You're right. It's a great question, Oscar. When would I be passing? So here's the deal. Voltage rating, you can always go up in voltage. No problem. You should never go down, obviously, but you can always go up in voltage. Capacitance, for the moment, I'm going to say that you want to keep this the same, as close as you can. As we go through the class, remember we've not been here very long. As we go through the class, I will point out to you specifically the places where you can change the number of microfarads. But for example, in many monitors, there's a capacitor whose whole job is to keep the sides straight. There's a capacitor that keeps the sides of the picture straight. If, as the capacitor fails, as it fails, I'll just leave it there, it causes the bottom to get smaller like that. We call that keystoning. It's a failure you might have even seen. We say that it is keystone. Keystone is like when you're building an arch out of bricks or stone. The top stone is shaped like that, isn't it? That's what holds the arch together. It's called the keystone. You pull the keystone out, the whole arch just disintegrates, right? So there's one capacitor whose job it is to keep the sides of the picture straight. If the capacitor fails, it pulls in like that. But if you replace it with a capacitor that has too many microfarads, it keystones the opposite direction, and you end up with that. So sometimes you have to keep exactly right. But if you are pretty darn close, you'll probably be all right almost always. But as we go through the class, we'll talk about this. It's a great question. It's a super great question. in general, it's pretty forgiving because electrolytic capacitors have a plus and minus like 20% tolerance. They're in microfarads. They're kind of way off in one way or another. But it's a great question, and I'll keep it in mind as we go through. Well, I always do anyway. Well, we'll talk about it. And finally, there's one more specification for capacitors that's pretty important. Easy to understand. It's the temperature rating. The temperature rating of the capacitor. And there's a whole bunch of different temperature ratings for capacitors, but in general, there are two main capacitor ratings. They are either 85 degrees, and of course it's Celsius, 85 degrees Celsius, or 105s. Either 85 degree capacitors or 105 degree capacitors. I personally would never, ever, ever, ever buy 85 degree capacitors. Of course, your situation's a little different. If you have a game that's on 24/7, you're really foolish if you use a lower temperature capacitor. When you open up the inside of a game, you know it's pretty hot inside there, and remember that's what's drying out capacitors, right? So if you have a higher temperature capacitor, it has a better hermetic seal. The bottom, the rubber plug that I pulled off the bottom of the capacitor, it's a better seal there, and I think that the electrolyte might be a different chemistry. I'm really not totally sure. But it is more expensive for the 105 degree capacitors. So if you're only looking at price, you're probably looking at 85 degree capacitors. Don't do that. There's one brand of capacitor that I highly recommend you get. It's the one that's in your sample bag. And the company is Nichicon. Nichicon. High quality Japanese capacitor, super high quality. That's what I use all the time. Another one is Panasonic. And those guys are pretty good too. And there's some other really good ones, but I would stick with Nichicon. They will definitely be more expensive. But they're cheap. It doesn't cost you very much to replace a bunch of capacitors. And it would be really foolish to skimp on the price of a capacitor just for 10 or 15 cents or something like that. That makes sense, doesn't it? So temperature is 105. So capacitance for the moment, I'm going to say let's keep that the same. Voltage, you can always go with a higher voltage capacitor. The temperature rating is the temperature rating. Makes sense, right?
And for the sake of asking,
Yeah.
if I place a lower voltage capacitor, what's the problem?
Dígame en inglés, por favor. Tell me to express that again, please.
Yeah. If I don't have the capacitor with the required voltage and I put a lower voltage,
I would never go down in voltage. No, that's nuts. What if it blows up? Now you don't know if it's
so
blowing.
that it blows up.
It might, yeah. If you put too low a voltage capacitor in there, I think it might. You would pierce the dielectric. I don't know. I've never done it, so I can't even imagine why you would do it. I know that would be bad mojo. I wouldn't do that. Is it difficult to obtain replacement components where you live?
Shipping is expensive. You always have to buy
From the United States?
Yeah.
Okay. I mean, I get everything shipped to me.
Sometimes I need one specific piece and I have
You have to buy 10.
a lot of.
Well, I never buy one of anything. If I'm replacing one part, I'm not going to order one because what if I put that in and whatever blew it out originally blows it out again? Now I don't have a replacement. So this is how I build a part stock. Not to get off the subject, but I'm a cheapskate. As you can tell, I'm a very cheap and dirty technician. I do this kind of stuff. I work with just a meter. I believe it's what you know that helps you fix stuff, not so much equipment, really. And the same holds true with components. I don't want to spend a bunch of money. We're going to talk more about this tomorrow. Buying a bunch of parts so I have everything. Oh, I have every part in the world. When something fails, I say to myself, well, I need this part. I'm just going to order 5 of them or 10 or whatever. And then I'll have extras. And so that's how I end up with extra ones. We'll talk about this more tomorrow. But I don't go out and buy a whole bunch of parts just to have the parts. I wait till something fails and then get a bunch of them. And in my opinion, generally speaking, when one thing has failed, quite a few things fail. Oh, hello. Is that a 360 degree?
Yeah, 360 camera.
Which one is that?
The Insta 360.
Oh, okay. I thought about getting that. I almost pressed the button and bought it. I've seen more videos, lots of videos using it. It's a great system.
Yeah, it's great.
It's really interesting.
I sent you the link.
Oh, okay.
The picture.
Yeah. Oh, okay.
Then you share it.
Okay. Thanks. Anyway, so I think we're getting close to lunchtime.
Lunch is ready.
Oh, it is. Okay. Okay. Entonces vámonos. Let's go. Let's go eat lunch, and let's see. Don't leave the premises for too long. We may start in a half an hour. We may restart in a half. Because there's no sense us sitting. Oh, wait a minute. Is the museum open? Can they play?
Yes.
Oh, never mind. Take an hour for lunch. Take an hour for lunch. All right. So let's take an hour for lunch, and we'll start up again. I forgot where we are. Right?
It's extra €2 per.
Om 2 betalen.
We're cheap too.
Let's see. You smoke? Yeah. You guys smoke too? I'm gonna go with you and have a smoke. I'll steal a cigarette.
How many machines do you have?
What? When I'm on the road, if someone will loan me a cigarette, I'll smoke.
So you got many more.
You can buy it.
Oh yeah. It was a hard relocation. Yeah. It wasn't that difficult. I started clock. So where do you guys go? Outside?
Well, most are like me, volunteers. So we're not paid. We do it just
For the love
for the love of Hassan. Hassan is, for the love of Hassan, because Hassan is.
Zo even.
De enige die erop zit is.
Nou, nee.
Oh, dat valt nog mee. Veel mensen naar de
Oh, opeens
studio.
wel. Toen ik laatst keek was er maar eentje. Die waren er allemaal. Die zijn er allemaal.
Hoe zijn die dag?
Oh, sorry.
Ja, dat maakt nog niet uit. We hebben toch geen gekke dingen over.
Nee, maar de oude in je dag.
Ja.
Hoe is het? Wie is dan daar?
Kan je muten trouwens?
Pas wel. Ja, hier.
Hoe goed zijn die? Ik ook niet van stuiten.
In.
En dat is goed genoeg om alles op te pikken.
Hoe lang is het nu?
Een uur. Want ze gaan ook even de zin kijken. Ja, goed voorgezet. Ja. Dan is dat al lang voor.